back. So this is the last talk in the complex methods or analytic methods in algebraic geometry. The speaker is Song Sun from the Institute of Advanced Study in Mathematics. And his title is Kähler-Ricci shrinkers and Fano fibrations.
Okay, thank you for the introduction, and thank the organizers for the invitation to give this talk. So my topic is on connection between differential geometry and algebraic geometry. So I should say this talk is based on joint work with Junsheng Zhang from NYU. He's a postdoc in NYU now. He was my former student. So since I was told to give this talk to slightly broader audience, I will structure my talk to spend a bit more time on the background. Then I will explain our result. This is just one theorem, and then we will explain a few conjectures. If we have time, I will explain the ideas of the proof. Please feel free to stop me if you have any questions. So a general theme in Kähler geometry is to explore the connections between a differential geometry and algebraic geometry. So basic fact, as everyone knows, is that if you have a compact complex manifold meeting a holomorphic line bundle with a Hermitian matrix with a positive curvature, then the manifold is biholomorphic to a projective algebraic subvariety of some Pn, and in a certain some canonical way. So then a curious question is, what about when the X is non-compact? So if you just ask this question naively, this is very difficult. For one thing, the X could have infinite topological type. So it cannot, in general, it cannot be quasi-projective. So we will return back to this question. So the upshot of this talk is we will prove a result for a class of such X. But the motivation comes from studying of canonical metrics. So I will explain. So the deeper results to connect the differential geometry and algebra is given by this Kempf-Ness type theorem. So it relates the solvability of certain geometric PDEs and algebraic stability. So this normally is infinite dimensional Kempf-Ness. So the finite dimensional Kempf-Ness version is as follows. So if you have a projective manifold ML and a Kähler metric in the first class of L, and if you have a compact group G acting on this data, so acting on M, preserving L lifts to L and preserving the metric omega, and with a moment map from M to the dual of the Lie algebra of G, then there's identification between these two sides. On the one left-hand side is the zero set of the moment map divided by the group G. So this is a compact Hausdorff set, and it comes with it could be singular, but ignoring singularities, it comes with a symplectic structure. And on the right, this type should be M semi-stable. So it's the complex quotient, GIT quotient of M by the complexified group of G. So this is algebraic geometry, and everyone knows it involves the GIT stability notion. So in infinite dimensional setting, then the G, everything is infinite dimensional. Formally, on the left-hand side, you are solving equation. It's mu equals 0. And infinite dimensional, it would be a PDE. And on the right-hand side, it's more curious. Like it's not a priori well-defined stability. So it's often a part of the problem is to look for the right stability condition to work with. There's two examples of this type. One is the classical theorem of Donaldson-Willenberg-Yao for holomorphic vector bundles. So if a holomorphic vector bundle over a compact Kähler manifold admits a unique Hermitian-Young-Mills connection, if and only if it is slope polystable. So here, this Hermitian-Young-Mills connection is viewed as a zero of the moment map, and then the stability condition is slope polystable. And formally, the group G is the gauge transformation group of a unitary connection. And there's a uniqueness here. So you link up to gauge equivalence. So for the slope polystable orbit, we get a unique canonical representative of Hermitian Young-Mills connection. And then this is a more recent work. It's about a decade ago. So Fano manifold admits a unique Kähler-Einstein metric if and only if it is a K polystable. Here, the equation is the Kähler-Einstein equation, and the stability condition is K polystability. The formally the group G is not diffeomorphism, it's a symplectic morphism group. These results have many new proofs and variants and generalizations. So I will focus on the second part, this Kähler-Einstein matrix. So Kähler-Einstein metric is a Kähler metric which satisfies this equation Ricci omega equals omega. And what this omega is, the metric is round in a sense. So I will not spend time explain the details of the equation, but it's just a canonical geometric PDE about the curvature of a Kähler metric. And then the notion of K stability, this a classical definition involves a test configuration and a Futaki invariant. So the question of finding a Kähler-Einstein metric can be viewed as finding a critical point of a convex function defined on a non-positive curved space. So the standard setup is a convex function, a strictly convex function on the real line R. So you want to know whether it has a critical point. So if on the first picture on the left, it's it has a critical point and it's a stable in the sense that you can test this whether the critical point exists by looking at the slope at the infinity along to the both directions. So it has to increase in both directions, and so this is to look at this direction going to infinity. That's the motivation for the test configurations, and this slope at infinity is the motivation for Futaki invariant. Here the first picture is stable and the Futaki invariant is positive. The slope is positive. As the second and the third one is not. There's no critical point, and the Futaki invariant, the slope in one direction towards the right is non-positive. The second one is negative, and the third one is 0. It's a kind of borderline case. It's semi-stable. It has no critical point, but you can think of it as a critical point at infinity. So I think the audience have seen many talks on K stability in this week and probably elsewhere. The definition nowadays in algebra, I think, have turned very algebraic. So a decade ago, when we proved this theorem, the K stability was supposed to be a mysterious notion in algebraic geometry, but clearly it's not the case right now due to the work of many algebraic geometers. It's very exciting to say this. But then we have a local version of this theorem. So we take the cone of a Fano manifold, then we reach flat if you take Kähler-Einstein, Fano Kähler-Einstein metric, then if you take cone over it, it's like the picture shown here, then you get a Ricci flat Kähler cone. So the standard example is you just take the CPN, you take cone over it, you get a flat CN+1 metric. It's a flat metric. And then the corresponding algebra geometric objects are K polystable Fano cones. So this equivalence was proved by Collins, Zacchetti, and Chi Li. So I will explain what is a Fano cone. It's a special. I mean, you can think of it as a affine cone over a Fano manifold or Fano variety, and there's a corresponding notion of K polystability. So so what is a Ricci flat Kähler cone? Is just a remaining cone. It's like really a cone. It has a scaling symmetry, and with which is Kähler. So it was a compatible complex structure. It's parallel. So on any cone, you have this radial direction, which is what I draw here. I write that negative j cos I, meaning that if I rotate this radial direction by the complex structure J, it will be tangential to the cross section of the cone, and that vector field is normally called the Reeb vector field, and that's cos I. If you apply J to this, you get cos I. So that's a it's an interesting fact that this is a Killing vector field that also preserve the complex structure. So it's a symmetry for both the metric and the complex structure. But in general, so this Killing vector field will generate a torus action, but in general could be of higher rank. It's not necessarily S1. If it generates S1, then your cone is just a algebraic. It's just affine. It's just affine cone over a Fano orbifold. But it could have it could generate a higher rank torus. So in this was an important work of Martelli, Spaziali in around 2006. They gave a volume minimization principle. A particular consequence that you can consider the ratio of the you can consider the volume if you have any remaining cone. There's a volume of the cross section distance 1 to the vertex. That's a invariant, and if you compare that with the volume of the standard sphere, then that's called the volume of the cone. So for Ricci flat Kähler cone, and it's shown that the volume is a algebraic number. In general, it may not be a rational number, but it's always algebraic, and this is based on the volume minimization principle they discovered. Okay, so but then this cone is kind of you can think of it as singularities with a symmetry, but in general you can just take consider a general singularities. So this was so started by Donaldson and me in 2015. So I gave a talk on this 10 years ago in this similar conference. So this is what we call two-step degeneration theory. So what the point is that in terms of the metric, so you suppose you have a singular Kähler-Einstein metric, and this is a natural setup is a non-collapse polarized Kähler-Einstein limit. But in any case, you can see that on the left of this picture is you can think of the metric with a singularity, and then in Riemannian geometry, it's very natural that we understand the singularity by zooming up. but it's by matrix rescaling, and it's by Cheeger-Collin theory. We know that passing to subsequent, we always end up with a cone, a remaining cone, if it's a remaining Einstein metric. But the difficulty is that this cone may not be unique in the sense that it may depend on the particular subsequence you choose when you do rescaling. So you can imagine you may see different cones in different scales. So this is usually a difficult question in geometric PDE analysis. But in any case, in this setup, we know that this cone was denoted by C is a affine algebraic variety. So the curious question we had is like we start with some algebraic singularity, it's XP, and then we end up with a cone. But this process is it depends on the metric. So and this C a priori may not be even unique depending you get many cones. But how do we understand this? We want to understand this in terms of algebraic geometry, and then what we discover is that there's a two-step degeneration. So the naive thing is you want to expect that maybe we can just understand this as a algebraic like scaling. So you can embed XP locally in some affine space and use some weights and then do a algebraic scaling. So there are two things here. First is that this weight, because this vector field may not generate C-star action. This weight may be irrational. It may not be integers. And the other thing is that we cannot do that in general. So what we instead we can do this first to get something which we call W. So this is a algebraic cone, but it's not may not agree with the metric tangent cone C we want to understand. And so then there's a second step, which is equivariant degeneration. Both they are cones, so it's a degeneration among cones, and it's a test configuration. It's like one parameter degeneration from W to C. So this W is a very interesting object because the C has a metric. You can think of it as polystable, but W it's purely comes from this algebraic rescaling, and this algebraic rescaling is canonically determined by the metric, but it itself does not emit a metric. So it's a kind of a semi-stable because then it further degenerates to a polystable limit. So it's the third picture in the showed for. So this is what we discovered. So we use this to prove the uniqueness of the metric tangent cone. And then we further conjecture that the W and the C are both they are algebraic invariants of singularities, which may lead to some local stability notion of singularities. And the first step is evaluation canonically determined by the metric. And then Chi soon afterwards gave an interpretation of this first step as a generalized volume minimization. So in terms of valuations, and then reformulated the conjecture in algebraic geometric terms. And the algebraic geometric theory has been studied and extensively studied, and by many people. I think it's not called stable degeneration theory. And then another interesting thing to study is that how do the singularities form? So before we study the singularity, we have a singularity, we can turn it into a cone if it's two-step. But then you may think of the singularities, if, for example, it come from smooth metrics. If you have sequence xi, omega I, pi converging to a long collapse limit x infinity, p infinity. So suppose we have a singularity formation, and then we don't just want to focus on the limited singularity itself. We want to understand how the singularity forms. Then what we do is you do not start with the limit space itself and rescale. We have to rescale while we converge. So this is so we rescale the whole sequence by a sequence lambda I go to infinity, and then what we obtain we can still obtain Ricci flat Kähler matrix as a limit, possibly with singularities and non-compact. But in general, they may not be cones. They may not have symmetry. And we call these objects bubbles. So it's known that they are affine varieties, and if you scale this back from infinity, you get something called asymptotic cones. So that are also cones. So it's some object which has a conical structure at infinity. So this is a rough picture of bubbling. So you on the top you see there's a sequence of spaces that smooth spaces that converge to something which is limited with singularity p infinity. And this during this process there is something, some, for example, here you see some topology that is I highlighted with this blue part is going to this point, so everything is shrinking. But then now I don't want this shrink on the bottom. I rescale each one so that this topology stays the same size. But then the whole space has to grow to infinity. What we obtain is this Z, which is a non-compact space. And at infinity, it looks like a cone. So itself is not a cone. It has some topology inside. One can iterate this procedure, and then we obtain a called bubble tree. So whenever singularity form, we can do this rescaling. But then in the next scale, they might have another singularity form. Then we will obtain this tree structures. So and then I showed 2 years ago that this bubble tree terminates in finite many steps. You don't get a infinite chain of this bubbling process. So an interesting question is to give an geometric description of this bubble tree as invariant, not for singularity, but for degeneration of singularities, KLT singularities, where this is pi is x over delta is a family of singularities, local singularity, and this base point we have when we rescale, we have to rescale based at the point. So here in algebraic setup, I think we choose a section of this fibration. So there are some work of Yuji Odaka in this direction, but I think it's still not completely understood how to describe this bubble tree purely algebra geometrically. But a simpler case is just a non-compact Ricci-flat Kähler metric itself, because if you have a non-compact Ricci-flat Kähler metric, you can always scale it down to form to scale down to a cone. The limit is a cone, and this is a singularity itself gives a singularity formation. So this non-compact Ricci-flat Kähler metric are normally called singularity models. So there's a dual degeneration theory from this affine variety to the cone at infinity. And so under some curvature decay assumption, so this earlier work of me and Junsheng, we discovered that it's easy, I mean, to know that there's a two-step degeneration. There's also this first semi-stable and then polystable. But what we discovered is that actually you only need a one step. You don't need two steps. This is a sharp contrast with the case of local singularities. This is for to understanding this metric asymptotic cones, what we call no semi-stability phenomena. But this is known only under curvature decaying assumption. Okay, so I will talk about this several instances of relating differential geometric objects, mainly K-lines and metrics, Ricci-flat Kähler cones, and this degenerations of metrics to algebraic geometric objects. So there is actually something similar for the Ricci flows. This is actually studied. This has been studied a long time ago. It's a work of Zhu Jian. It's called Songtian program. So here you take a say projective manifold XL, choose a Kähler metric and run the Ricci flow. So you deform the metric along the negative of the Ricci direction of the Ricci curvature. So this is in general, Ricci flow is difficult to study, but in this Kähler case, if you take the cohomology class, we know it has a priori determined by the first chain class of L and of the canonical class, and it's a theorem that there's a maximum existence time, so it's a maximum time when for it to reach a singularity is given by numerically by this number T max, and T max equals infinity if and only for Kx is F, it's a minimum model. So it has a clear relationship with the minimum model program. It's kind of geometrization of the minimum model program. So suppose we have a finite time singularity, T max is less than infinity, then algebraically, this is from minimum model program. We know that there's a Fano fibration, which is either a birational contraction or a Mori fibration. So it can you may so I will this Fano fibration should be known to the expert, but I will record the definition later. But roughly speaking, it's a fibration where the fibers are Fano. But then it's not, so I think the two typical pictures are on the left is a birational contraction, so it's a birational map with contracting devices or lower dimensional subvarieties. And on the right, it's a fibration. You may have a singular fibers. The fibers are Fano, Mori fibration. So this is well understood. But in terms of Ricci flow, geometrically, we will encounter a singularity of Ricci flow at this time T max, and the mechanism of this singularity formation is expected to be given by a metric contraction. It's on the left. Metrically, you want to contract the divisor, and on metric is contract the fibers of the fibration. But this is in general not known. So, but if you view this Ricci flow as a differential equation, it's a parabolic equation, and there's a similar similar idea of understanding this singularity by rescaling. It's like this local singularity I discussed before. So this you view this this singularity as a singularity of the space time. So it's x times this interval, and then we want to do parabolic rescaling. So you scale both the space direction and the time direction. One expects to get some self-similar Ricci flow limits. It's like this cones in the for the Kähler-Einstein singularity case, and they are generated by so-called shrinking gradient Ricci solitons. I will explain this all this later. So this is much harder, and this three-dimension is work of Perelman and his proof of the Poincaré conjecture. And then my former colleague Richard Bamler has a generalization of these statements to higher dimensions. So you can do suitable rescalings together this Ricci solitons. But these Ricci solitons themselves maybe have singularities, but more severely they may be non-compact. So now I will introduce the main players of the title of this talk. So this is a Riemannian geometric notion. A gradient Ricci soliton is a Riemannian metric G, satisfying this equation, the Ricci of G plus the Hessian of the function of a function f equals lambda G. So if the function is constant, then it's just a Einstein metric which is proportional to the metric tensor. But with this function, it's called a Ricci-Soliton. Meaning that if you use the diffeomorphism generated by the gradient of the function, and then you pull back the this metric G by this sequence of diffeomorphisms with suitable speed, then we will get a Ricci flow. So that's it's a Ricci flow, but it's self-similar. It different times. They're not exactly the same as the tensors, but they differ by diffeomorphism. And this sign of lambda determines whether this metric as a tensor is shrinking or steady or expanding. So lambda positive means shrinking. Lambda equals 0 is steady, and lambda negative is expanding. So this is general notion in Riemannian geometry. In the Kähler case, if you further assume the metric G is Kähler, then this equation can be decoupled into two equations. It's a Hessian of F. Now you can decompose into 1,1 type and 2,0,0,2 type. So it turns out there's a 0,2 type of this because the Ricci and the metric they are 1,1 type. So then the 0,2 type only involves the function f, and this is equivalent to saying that the J gradient f is a holomorphic Killing vector field. You automatically get a symmetry on the complex structure and on the metric. This is data. So this data of f is, you can, if you turn into this vector field, Xi is essentially complex geometric data. You can prescribe it complex geometrically. But then the 1,1 part is an equation, which is the Ricci plus the dd bar part of f equals lambda omega. And so this is a elliptic partial differential equation, and you can take the cohomology class. You see that the first chain class of X is proportional to the first chain class of this Kähler metric omega, even when this works even for non-compact X. So if X is compact, then we know pretty well. So if Xi equals 0, then the vector field is vanished. Then there's no F. What you get is just a Kähler-Einstein metric. When lambda equals 0, you get a Calabi-Yau matrix. When Xi is not 0, then we will have, so that the manifold have to admit a non-trivial holomorphic vector field, and its first chain class has definite sign. So it implies that lambda has to be positive, and X has to be Fano. In particular, it is projective. So in both cases, we have canonical geometric structures studied. So these are so I talk about this Kähler-Einstein metrics in the Fano case relate to case stability, and this Kähler-Ricci solitons in Fano manifold, they also relate to generalized stability. But if X is non-compact, then the situation is much more subtle. The sign, first, the sign is not well defined. For example, the standard metric on Cn, flat metric on Cn, because it's dd bar exact, so you can view it as a Ricci soliton for any lambda. So it's not really, does not make sense to talk about the sign of lambda a priori. And if you consider the case when lambda equals 0 and Xi equals 0, this is just a complete Calabi-Yau matrix. So this there was conjecture of Yau that this complete Calabi-Yau matrix can be compactified, but that's turned out to be not true in general. So the topology could be infinite, even the complex dimension is 2. So assuming some Euclidean volume growth condition, there are some conjectural connection to algebraic geometry, but still we don't know in general. And also the uniqueness part also fails severely when lambda is not positive. So even on Cn you can have many Kähler-Ricci shrinkers with with lambda negative. And from the analysis point of view, a non-compact manifold analysis in general is not well posed unless some geometric information is prescribed at infinity. So in this talk, so we will not consider the case lambda is a non-positive because of all these issues. When lambda is positive, we discover that there is a connection to algebraic geometry. So we can normalize lambda equals 1, and then the equation becomes Ricci plus square root minus 1 of partial part of r f equals omega. Such a omega is, for simplicity of terminology, we call it Kähler-Ricci shrinker. It's a shrinking soliton. So here there are two special cases. Either we let the vector field psi equals 0, so this dd bar f term does not exist, then we get Ricci equals omega, and then this implies this metric is complete. It has to be compact, and it's actually a Kähler-Einstein metric on a Fano manifold. We know then it's projective, but we can also let the other term Ricci to be 0. Then the metric G becomes a Hessian of f, and this is a Ricci flat metric, but it's also a Kähler cone because it's Hessian. G is a Hessian of a function. So this is Ricci flat Kähler cone metric. We're going back to beginning. This actually is known that a Kähler cone is a Riemannian cone. If it's Kähler, then it's naturally a affine variety. This was a result proved by Van Covering in 2011. So there is actually hope to connect to algebraic geometry. There's two special cases. So what we prove is this result for general Kähler-Ricci shrinkers. We build a connection to algebraic geometry. We show that a Kähler-Ricci shrinker is naturally a quasi-projective variety. In particular, its X is of finite topological type. So that's not even known before without first proving it's a quasi-projective variety. So if you compare this with the case of complete Calabi-Yau matrix, this shows that in this case, previously, informally, I call this a non-compact Fano manifold. It behaves much better. So this is a theorem. So I should say that in compact dimension 2, there actually a complete classification of Kähler-Ricci shrinkers by recent work of many people. It's finished with the work of Yu Li and Bing Wang, 2025. So in the compact, you have the diapedral surface. In non-compact, there are only 4 examples. It's a C2, C times CP1. It's a blow up of C2 at the point, or blow up of C times CP1 at the point. So it's also the last one. The construction of such a Kähler shrinker is also not easy. So to explain the content of the main result, we need to recall and introduce several terminologies. So first is a notion of Fano fibration. As I said, it's a projective morphism between normal varieties with connected fibers. And so upstairs we have KLT singularities and the relative canonical devices anti-ample. And so in our case, we are interested in the germ in the local. What is the local of local Fano fibration? Is actually just a neighborhood of a fiber. Just fix a point P. So special cases when this map is identity, then this is just a KLT singularity, and when the base is a point, then it's just a Fano variety. So but this Kähler-Ricci shrinker stuff, we need a symmetry. So we need to introduce what is a polarized Fano fibration. So this we have to first do a polarized affine cone. So it's an affine variety with a compact torus action with a unique fixed point, and then we need to choose a Riemann vector field, psi, with acting with positive weights on so it behaves like a cone. But then this vector field does not have to be does not have to be rational. This is a algebraic setup that was introduced by Collins Zakility to study kilocones in Sasaki geometry. So if here we don't require Y to have KLT singularity. If Y have KLT singularity, then it's called a Fano cone. So a polarized Fano fibration will consist of a Fano fibration whose base is a polarized affine cone, and then this vector field, this action lifts upstairs. So it's an equivalent torus action on X and Y, and an element in the Lie algebra of the torus. So such that the base is a polarized affine cone. It's a so this picture, so Y I just drew it's one direction. It's a cone, and then X is something over Y. So this thing itself is a polarized Fano fibration, and this vector field on Y lifts to X, but on X it may not have a unique fixed point. So special cases are, again, if the pi is identity map, this is a Fano cone, and if Y is a point, then this is what we call the polarized Fano variety, which means it's a Fano variety together with a choice of vector field. So the precise statement of the theorem is that the Kähler-Ricci shrinker naturally defines a polarized Fano fibration, and then a polarized Fano fibration is quasi-projective. And using this, it's proved by independently by us and my student Carlos Esparza that a Kähler-Ricci shrinker is simply connected. So it's a generalization of the fact that a Fano variety is simply connected. Fano manifold is simply connected. Kähler-Ricci soliton, compact Kähler-Ricci shrinker is simply connected. That uses the fact that the Fano manifold is simply connected. So a traditional method for proving this goes by constructing holomorphic functions. I mean, to proving that something is quasi-projective is you need to construct holomorphic objects, holomorphic functions, or holomorphic sections. And that will require, normally the analysis is not sufficient. It often requires actual assumptions on the geometry at infinity. So our proof instead uses the symplectic geometry and the birational geometry. If I have time, I will explain. I should go that there's some open questions after this theorem that we can now really study the Kähler-Ricci shrinkers on a polarized Fano fibration. It's a differential geometric object. So we can ask whether a polarized Fano fibration admits such a differential geometric object, Kähler-Ricci shrinker. And then there's a notion, one can define notion of K stability, and it turns out that this that we have conjecture that there's a polarized Fano fibration, and that means a Kähler-Ricci shrinker if and only if it is K polystable, and this if it exists, it has to be unique. So this gives a unification of this Yao-Tian-Donaldson type conjectures for Kähler-Einstein matrix, Ricci flat Kähler-Cone matrix, and the compact Kähler-Ricci shrinkers. So all these three have, I think, essentially been established. But this non-compact setting is more complicated. Even the uniqueness question is quite non-trivial. So I have two students writing thesis on this uniqueness question. So Charles Cifarelli proved that the uniqueness in the toric case, and the student Carlos Esparza proved that the uniqueness under this curvature assumption decay. Curvature decay assumption, the quadratic curvature decays quadratically fast. So on a polarized Fano fibration, there's a notion of a weighted volume function on the space of Reeb vector fields. So when we started working on this with Connor and Durrell a few years ago on non-compact Kähler-Ricci shrinkers, we introduced this notion of weighted volume using symplectic geometry. So it's essentially, so this integral over x of e to the negative mu eta mu pairing, we say that the mu is a moment map for this action of t with respect to symplectic form omega. So this the point is that in the compact case, this is certainly well defined, and in non-compact case, we have to make sense of this, and that uses Twist-Hickman localization formula, and it generalizes the notion of volume of Sasaki manifolds by Martelli, Sparks, Yao, and the weighted volume on a polarized Fano variety by Tianzhu, and it's for a Kähler-Ricci shrinker, it reduces to Perelman's mu entropy. So this is an interesting notion. So algebraically for Fano fibration germ, one can define a weighted volume for valuations centered on the central fiber and using the theory of Okonkov bodies, just a slight generalization of the case of KLT singularities. And the weighted volume is defined to be the minimum weighted volume. Weighted volume of a polarized of a Fano vibration is defined to be the weighted volume among all valuations centered on this, and this extends the notion of a normalized volume of a KLT singularity and the notion of beta tilde invariant on a Fano variety. So studied by Chile and others. So this is a slight generalization of Chile's definition. But then the next conjecture is the relation between the two singularities of Kähler-Ricci flows and algebraic stability. So we know if we have a finite singularity by model program, we know there's a Fano vibration. And then how do we understand this shrinkers coming from the Ricci flow using this Fano vibration? So we propose a two-step degeneration for Kähler-Ricci flows. So so it's similar to the case of singularities of Kähler-Einstein matrix. So using instead, so there you from a singularity we get a cone. Here we for Fano vibration germ we get a polarized Fano vibration. We have to do two steps: first to semi-stable and then to polystable, and one can make a purely algebraic geometric conjecture. So this also unifies some previous work on the singularities of Kähler-Einstein matrix and the normalized limits of Ricci flow on Fano manifolds. That was studied independently before, independent of this singularities of Kähler-Einstein matrix, and now we see that they are actually it should be fit into one framework, and the weighted volume of a Fano vibrating germ, I think it's an interesting algebraic invariant that is worth studying in the future. So last minute, I just explained that want to say that in the proof of this result, the key point is to show that this function f, so Ricci plus partial bar f equals omega, it has a compact critical set, and for this we have to use the result of Burka on the boundariness of Fano type varieties, and another result of Bloom and Liu on the semi-continuity of local volume of KLT singularities. So I have this is the picture for the proof. So I don't think I have time to explain it, but it goes by symplectic reduction and studying the birational transformation between the symplectic quotient after passing through critical values. Okay, I think I'm done here. And thanks for your attention.
For the questions, I have to see. So, are there any questions? So if we use the microphone like this, can you hear us?
Yes.
Okay, then that's great.
So in the case when there is a Kähler-Ricci shrinker on polarized Fano vibration, is there some sort of a canonical metric on the base cone that gives you some sort of onsets?
That's a very good question. So unfortunately, no. So that's a point. That's why we can expect this uniqueness. So and why this uniqueness is interesting. So there normally, I mean, if you have a Kähler-Ricci shrinker, there you can, for example, if you have a quadratic curvature decay, you can get a cone at a metric cone at infinity, but this cone normally does not satisfy equation. The point is that this Ricci, go back to the equation. If you scale down this equation, what you get is the Ricci term disappear. What you get just is a cone. So you should think of this this metric at infinity should be some part of the data you need to solve. It's not something you can prescribe. Otherwise, it will not be unique if you can prescribe cones. So it's kind of a free boundary problem in the PDE. So it's the data at infinity is determined by the solution itself.
Thank you.
Mm-hmm.
Any more questions? Okay, seems not to be the case. So let's thank Song again for this talk, and then our session concludes.
Thank you.
Hey, thanks very much.
Thanks. Okay, see you.
Yeah, I'll see you.
Bye.
How do I?